Welcome to this lesson on cameras and how they capture light to form images. A camera is one of the most remarkable applications of optical principles in everyday life. In this series, we'll explore the fascinating physics behind how cameras work, from the journey of light through the lens to the final image formation on a sensor. By the end of this lesson, you'll understand the key components that make photography possible and how they all work together to freeze moments in time. Let's begin with a fundamental question. What exactly is a camera? A camera is an optical instrument that captures and records images by controlling how light enters and focuses onto a light-sensitive surface. Think of it as a sophisticated tool that harnesses the behavior of light to create visual representations of the world around us. The camera's primary function is to gather light rays from objects in a scene, focus them precisely, and convert them into a permanent image. This process involves careful manipulation of light, using various optical and mechanical components working in perfect harmony. Every camera, whether it's a simple smartphone camera or a professional digital single-lens reflex camera, relies on four essential components. First, the lens system focuses incoming light rays from the scene onto a specific point. Second, the aperture controls the intensity of light entering the camera, much like how the pupil of your eye expands and contracts. Third, the shutter controls the duration for which light is allowed to reach the sensor, determining how long the exposure lasts. Finally, the image sensor captures the focused image and converts it into a digital or chemical record. Each of these components plays a crucial role in producing high-quality photographs. The lens is arguably the most critical component of any camera. Its primary function is to converge light rays from the object to form a real inverted image on the sensor or film. Camera lenses are typically converging or convex lenses, which means they bend light rays inward to meet at a focal point. The focal length of the lens determines both the magnification and the field of view of the captured image. To achieve the highest image quality, modern camera lenses use multiple lens elements arranged in specific configurations. This complex arrangement helps reduce optical aberrations such as distortion, chromatic aberration, and blurring, ensuring that the final image is sharp and accurately represents the scene. The relationship between the lens, the object, and the image formed is described mathematically by the thin lens equation. This equation states that 1 over f equals 1 over v minus 1 over u, where f represents the focal length of the lens, v represents the image distance from the lens to where the image is formed, and u represents the object distance from the lens to the object being photographed. This fundamental formula helps photographers and optical engineers understand exactly where an image will form based on the position of the object and the characteristics of the lens. In a camera, the lens is adjusted to ensure that the image forms precisely on the sensor plane, creating a sharp, focused photograph. The aperture, measured using f-numbers, controls the diameter of the lens opening, which directly regulates both light intensity and depth of field. The f-number is calculated as the focal length divided by the effective diameter of the aperture opening. Now, here's something counterintuitive. A small f-number actually means a large aperture opening, while a large f-number means a small aperture opening. The aperture has a significant effect on the final image. A small aperture, indicated by a large f-number like f22, produces a greater depth of field, meaning more of the scene from foreground to background appears in sharp focus. Conversely, a large aperture, indicated by a small f-number like f2, creates a shallow depth of field, where only the subject is sharp while the background becomes beautifully blurred. The shutter is a mechanical or electronic device that controls the duration of light exposure to the sensor. Shutter speed determines two critical aspects of your photograph: motion capture and overall brightness. A fast shutter speed, such as 1/1000th of a second, freezes motion and is ideal for capturing fast-moving subjects like athletes or wildlife. However, because the shutter is open for such a short time, less light reaches the sensor. On the other hand, a slow shutter speed, such as 1 second or longer, allows more light to reach the sensor, making it suitable for low-light conditions. The trade-off is that any movement during this longer exposure will appear as motion blur in the final image. Photographers balance shutter speed with aperture and sensor sensitivity to achieve the perfect exposure. Once light has passed through the lens, aperture, and shutter, it reaches the image sensor, which is the heart of digital photography. The image sensor converts the optical image into electrical signals using millions of tiny light-sensitive elements called photodiodes, arranged in a pixel array. Each photodiode captures light and generates an electrical charge proportional to the light intensity. There are two main types of image sensors used in modern cameras. The charge-coupled device, or CCD sensor, is known for producing high-quality images with excellent color accuracy, though it has a slower readout speed and consumes more power. The complementary metal oxide semiconductor, or CMOS sensor, offers faster performance, lower power consumption, and is more energy efficient, making it the preferred choice for most contemporary digital cameras. Image resolution is determined by the number of pixels in the sensor array. For example, a 12-megapixel camera sensor contains 12 million individual pixels, each capturing a tiny portion of the scene. While higher resolution generally allows for more detail and larger print sizes, resolution alone doesn't guarantee image quality. Several other factors significantly influence the final image quality. The physical size of individual pixels and the overall sensor dimensions affect light gathering ability and noise performance. Lens quality and the presence of optical aberrations determine how sharply light is focused onto the sensor. Finally, the signal-to-noise ratio, which compares the actual image information to random electronic noise, plays a crucial role in producing clean, detailed photographs, especially in low-light conditions. Let's review the key concepts we've covered in this lesson. First, cameras use converging lenses to form real, inverted images on a sensor or film, applying fundamental principles of optics to capture scenes from the real world. Second, the aperture controls both light intensity entering the camera and depth of field, allowing photographers to create images with selective focus. Third, shutter speed determines the exposure time and affects motion capture, giving creative control over how movement is represented. Fourth, image sensors convert light into electrical signals using sophisticated photodiode arrays, with CCD and CMOS being the two primary technologies. Finally, image quality depends on multiple factors including sensor resolution, pixel size, lens quality, and signal-to-noise ratio, all working together to produce stunning photographs. Understanding these principles gives you a solid foundation in camera optics and image formation.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.